Okay, let's start. Yes. Okay, so thank you very much for joining me today. We have a seminar that is going to be held by Paulo Lopes, which is a professor currently working at the Observatorio of Valongo in Rio de Janeiro. And he will be talking about his last work published in 2024, I think, about the role of groups in galaxy evolution, more specifically about the importance of preprocessing in galaxies in groups. So thank you very much, Paulo.
Thank you, Anna. So thank you very much for the opportunity of being here and give this presentation today. So that's the work that I'm going to talk about. It's a letter that we published last year. And let's see. So the motivation for this work, here we have
we have a stick somewhere.
Yeah, okay.
Where did the stick go?
So we have here a polar mass diagram showing the galaxy distribution in the local universe. And as you can see, we have some well-known populations, such as that's fine over there, such as the blue cloud and the red sequence. And we have different phenomena that affect galaxy evolution when they migrate most of times from the blue cloud to the red sequence. So supernova is more important than supernova feedback, more important for lower mass systems, while AGN feedback is more important for the more massive galaxies. And in the higher density environment, we find normally red galaxies with low star formation or zero. And in the low density environment, we normally find the opposite blue galaxies. That are responsible for driving the quenching that are related to the mass of the galaxies or to the environment where they live. So on what regards the environment, which is what I'm more focused on the talk here today for this talk. So we have some mechanisms that are more effective in the central parts of clusters and some others that are more effective in lower density regions, but not in the field. So intermediate regions such as groups. For instance, mergers are more common in groups or in the outskirts of clusters due to the high velocity that we have between cluster members in the central parts. So we don't expect mergers, a high fraction of mergers in the central parts of clusters, but that's more common within groups where their relative velocities are lower. Okay, so and the particular the topic that I'm going to talk about is about preprocessing. That's a phenomenon that's has been named since the 90s after this works. Zabudov et al. 1996, Fujita 2004, and which is it's a phenomenon that's named after the fast aging of part of galaxies that lie within clusters that come to the clusters within groups. So the term is related to the preprocessing, the faster evolution that these galaxies have within the group environment before they arrive in clusters. So this has been extensively investigated in the past years using both simulations and/or observations. So here we have a picture from Bai et al. 2013. Using simulations, we can see here a cluster, and the galaxies within it out to 5 are 200. So the circles mark 1, 2, 3, 4, 5 are 200. And galaxies are separate between galaxies that haven't been preprocessed, so galaxies that are arriving to the clusters with a higher star formation than the other part of galaxies. And the galaxies that are colored are galaxies that are part of groups that are falling into the clusters. And you can see a few groups there within the cluster region. So we have these two populations of galaxies that can way to separate the galaxies within the clusters. What I call, some people call non-group galaxies, I call individual galaxies, and the others the group galaxies. We see that in observational data. Here's data from XMM, from this paper from Haynes et al. In 2018, where they search for groups in the surrounding regions of clusters at redshift around 0.3. And so, for instance, here we have a ABL 1763. The redshift is actually 0.223. And they list here a few other systems that they have the red circles. They indicate groups that are also detected in X-rays at the same redshift as the cluster. I have there one in the background that's a redshift 0.48, but it's not marked as a simple. It's a low mass cluster with 10 to 14 solar masses, for instance. Going back to the work that I showed before, another way to see that is searching for the fraction of galaxies that being satellites of halos with mass above 10 to 13 solar masses, so mass typical of groups, other than the host as a function of galaxy position and time at the time of observation. So, for instance, if you see the right line there, it's for massive clusters, typical of coma, 10 to 15 solar mass, and we see the fraction of galaxies that belong to another host with lower mass than 10 to 15, but above 10 to 13 in the past. So we see that for coma-like clusters, within R200, that's something like 60% of the galaxies arrived in the clusters as part of subgroups in the past. And for lower mass systems, the fraction is smaller. For instance, if you see the green line and the blue line, they are for lower mass systems than coma. And the preprocessing effect is normally characterized in observational data, looking for the variation of a given property or a given population of galaxies as a function of clustercentric distance. So here we have the fraction of star-forming galaxies measured in 2 ways using the infrared or a color estimate. And as a function of clustercentric distance going all the way to 5 R200, that's shown in the bottom. In the top, that's roughly 3 R200 of the cluster. That's for a stacked sample of clusters from Haynes et al. 2015. And you see that even if you go all the way to 3 R200, the fraction of star-forming galaxies never reach the field level, which is marked by a horizontal line on the top there. So we can see that this difference is attributed to the preprocessing effect, so that the galaxies in groups are responsible to quenching part of the galaxies of the cluster population in the outskirts before they arrive into the clusters. So, sorry, keep this plot in mind. I'm going to show some results that are in a similar way to this one later on. So where to go when investigating the preprocessing effect? So in the past, most of the studies of clusters, they were concentrating in the core of clusters, or at most going to R200 or the virial radius. And as time goes by, we have more studies going to the outskirts, going all the way to the turnaround radius, where we still have matter falling to the cluster, which is roughly 5 times R200. And beyond that, you have the field that can be in different sorts of environment. That's another way to see here. This in the very central part, you have an image of the brightest galaxies of the coma cluster, and you have the X-ray emission superimposed there. Most of the X-ray emission is within R500 in red, and then we have R200, which is close to the virial range, not exactly. And you have this black circle showing 3 R200. So what we want to probe is even beyond all the way to 5 R200. So the data that we use, you have a sample of 238 clusters, but in the end we work with 153 that have at least 20 galaxies as members. The objects are between 0.03 and 0.1. That is low on data. And surrounding these 153 galaxy clusters, we have 641 groups that are within that turnaround radius. And we split galaxies between individual and group galaxies inside the cluster. So whatever is not part of a group that's a member of a cluster, we call individual galaxy, a galaxy that's arriving in a cluster by itself. And we have two control samples. Instead of only having the field, we also have a sample of isolated groups that hasn't been shown in the past before. And the group sample was selected using a friends of friends algorithm from Tempo et al. 2012. And we restrict this work to bright galaxies, brighter than star plus 1. So we have to classify galaxies as passive or star forming. We simply use this diagram, the log of star formation rate versus stellar mass. And we consider galaxies as passive as those that are below this first line here. They are passive, and above they are called star forming. And in the middle of the two lines, if you want to have something like a green value, you could also have. So in the left plot, we have field galaxies. In the right plot, we have cluster galaxies. So you can see that the distribution is very different. And so for our sample of 153 clusters, we have here the projected phase space, the relative velocity on the line of sight as a function of cluster-centric distance all the way to R500. And we have on the left individual galaxies, on the right the group galaxies. And as you can see, the distribution is very different. So the individual galaxies are more concentrated within R200 or at the most 2 R200, while the group galaxies, they are more to the outskirts. So that's perhaps the main result that we have. So we showed similar to that plot from Haynes et al. 2015, the fraction of star-forming galaxies as a function of cluster-centric distance. But instead of going all the way to 3 R200, we go all the way to 5 R200 here. And the black points are all cluster galaxies. And those are the ones that should be compared to the results of Haynes et al. And some others in the literature. So we see that at 3 R200, where they are in that paper, we are well below the field level, which is the horizontal line on the top. But if you go all the way to 5 R200, the black points are still below. So even if you go all the way to 5 R200, we don't get there. But if you split the black squares, all cluster galaxies, individual and group galaxies, then we see that this decrease in the fraction of star-forming galaxies is all attributed to the group galaxies that are in red here, while the individual galaxies, they kind of reach the field level when we go to 5 R200. And another interesting result here is that we have the isolated groups, the horizontal line here, and we can see that even the isolated groups that are not part of the infalling region of clusters, they already show a reduced fraction of star formation in comparison to the field. Let me see what's important here. So that's the first time that we show this result all the way to 5 R200 and splitting galaxies between individual and non-group galaxies, or no, between individual and group galaxies. There are some other results in the literature that they have the separation, but they don't go to 5 R200. And I think there are a few results that go to 5 R200, but not showing the separation. So that's the first time that we can reach an agreement between the field and cluster count for individual galaxies. And also this compares to the isolated group sample, something new, showing also this reduced diffraction for these objects. Here we have the local galaxy density, this parameter sigma 5, just the number density of galaxies measured for each galaxy of our sample as a function of cluster-centric distance, and the symbols are the same. And as we can see, this effect is explained by the higher density environment of the group galaxies in red in comparison to the individual galaxies that are infalling to the cluster. So once these galaxies they go to the central parts of the cluster, the local environment tends to increase, and that explains the reduced star formation that they have once or the quenching process that they suffer once they go to the inner parts of the cluster. But in the outskirts, the difference could be explained by this parameter, the local galaxy density. Another interesting result that we got is this one. So it's the same kind of plot that we had before, but here we just show the group galaxies. And the group galaxies are splitting between, according to their mass, the mass of the groups, or the number of members. So we show pairs and triplets here in red, systems with at least 3 galaxies, systems with between 3 and 10 in green, and more massive groups with more than 10 galaxies in black. And as we can see here, even for, so we can see here there is a difference between the fraction of star-forming galaxies as a function of group mass. So the groups that are falling in the cluster, they contribute differently to this reprocessing scenario, and that depends on the mass of the systems. But another interesting thing is that even for pairs and triplets, we already see a difference to the field. So even small groups, such as pairs and triplets, they contribute to this effect. So their counts are way below the field level. Okay.
Can you please come back to the first bin of triplets or group galaxies goes up in the fraction of the star-forming galaxies?
Here that you see?
Yes. So all the curves are falling, but that one's increasing the center.
The green one?
Yep.
Yeah. Yeah, so let's see within the error bars of the others for outside. But the main difficulty here, the results within R200, we have more concern with them because it's difficult to detect the groups inside the clusters in the very central region. It's something more difficult to do that. So these results are less reliable. But I see your point, but they are still within the error bars in any case. Let's send most nets here. So that's a comment for the following plot. So here we investigate this difference not only as a fraction of star-forming galaxies, but the properties of the galaxy, such as the M4000 parameter, H delta, and so on, morphological type, and so. But also we check here for the fraction of late-type galaxies using the classification from Dominguez Sanchez et al. A few years ago. And so that's a similar plot, but showing the fraction of late-type galaxies as a function of radius. And we see the same difference between group galaxies and individual galaxies. We notice here that the fraction are typically larger than we got for the fraction of star-forming galaxies, and we interpreted that as a longer time scale for the morphological transformation to happen in comparison to the quenching process. But that's something that depends on where we split galaxies between late and early type. So we kind of redid this result, and the result is not that this conclusion here is not that significant from what we recently checked. Okay, so going to this discussion here. Here we have clustercentric plot again. I would like to highlight this region here with this green ellipse, where there is this difference here, this inversion of the trend. So the group galaxies they go above the individual galaxies in that region around 1 at 200. And we don't really know the reason for that, but we have a few things that we discussed in the paper. I'm going to get there. One of the things actually is the attributed to the group mass that we can sample. So, for instance, we have this result from Bian Pony et al. 2018, where they use that work from Haynes et al. 2018, where they have this XMM data for groups around clusters around redshift 0.2, 0.3. And so they don't get this inversion that we found, but the mass that they probe for the groups is much higher than what we can probe, because they need X-ray selection. So they don't have X-rays for lower mass groups, and even think for systems below 5 galaxies or pairs or triples, they wouldn't have at all. So that would be one thing. This is the work that I showed before, another cluster here. And also the sample that they have is limited to a much smaller region. So they have infalling groups between 0.4 or so, 0.3 and 1.3 at 200 only. Because of the small field of view of XMN, you can't go wider than that, even being at redshift 0.2 or 3. Another reason that could explain that effect is the backsplash galaxy. So here in the left there, we have the relative velocity from simulations, from the Millennium simulation. And galaxies are split in different populations. The two that I highlight here are the infalling galaxies in blue, and the backsplash galaxies that are mostly in green there. The color here is not it's not exactly for the populations, the time when the galaxies are created by the cluster, but you can see the infalling galaxies mostly in blue, and the backsplash galaxies they are mostly in green and lime or something like that. And those are galaxies that pass the center of the cluster once and come back, comprising this population of backsplash galaxies. When you see in observations, that's what we see, because we have line of sight velocity, so it's a projected velocity, and cluster-centric radius is a projected offset too. So the backsplash galaxies, they are all mixed up here, and they go from around 1, some studies go to 3 or 4 at 200. That's splitting the populations. I'm going to skip that. So what we did is we checked. So there are some observational results compared to simulations that show that the backsplash galaxies, when you looked in the observations, they would have low velocities along the line of sight, low velocity offsets compared to the cluster center. So backsplash galaxies would have low velocity compared to the rest of the galaxies. So we split the galaxies between low velocity and high velocity. I'm sorry, I forgot which cuts of velocity I used it here. And they are between 1 and 2 at 200. So to try to sample this part here that's highlighted. And we see here, oh gosh, I want right away. We see here that for the low velocity, so galaxies could be backsplash, we see that the individual galaxies in blue and the group galaxies in red, and we see a difference in the specific star formation rate. So the blue galaxies, the individual ones, they have a reduced star formation in comparison to the group. When you check the high velocity, we have no indication for a difference between the two distributions. So that could explain in part at least that this effect here. So some of the galaxies, the individual galaxies, they are actually galaxies that went through the cluster. They were quenching in this process, and they come back as quench. And we don't know when they looked at the individual galaxies at around 1, 2, or 200, if they are arriving for the first time, or there's a mix of the populations when we check the observations. And there's another possibility. It's the shield effect that it's from a paper from a few years ago, but that I don't know how to pronounce it very well, about 2022, using TNG data, where they claim that the galaxies that are arriving to the central parts of clusters through filaments and belonging to groups, they would have like a shield effect from the gas within the filaments and also mainly the gas from the groups. So they would have a delay on their quenching in comparison to galaxies that are arriving outside filaments, outside groups. So that's a claim that they have. So we know that clusters are fed by filaments. We have many works pointing to that. And actually, when we see the investigation of the preprocessing effect in galaxies with filaments, we have the opposite of what Fecha proposed. So we see that the passive fraction increases as we go to the center, as expected to the center of the clusters, but it's higher for galaxies with filaments. So it's the opposite actually of what Fecha proposed. Looking at our data, we try to detect that with separate galaxies that are the individual galaxies, the group galaxies. We check which of them are part or not of filaments. And we see that galaxies that are in filaments, the ones that are for the groups, there in the left, in red, they have a higher star formation rate than the ones that are individual. So there is a slight indication that the shield effect could also be affected, but I don't think it's too strong here. This is probably better studied with simulations as they showed. And here for the galaxies outside filaments, we don't see a significant difference between the specific star formation rates of individual and group galaxies. That's ongoing work. It's not published, and so I'm going just to talk about some ongoing work here that we've been doing. So dependence on stellar mass. So what I showed before was for galaxies that are bright galaxies and brighter than star plus 1. So most galaxies have stellar mass above 10 log of the stellar mass larger than 10. And here we split in, so we redefined our sample. We didn't impose a cut of the luminosity cut again, the M star plus 1. And we have all galaxies with masses larger than 9 in log scale. That's shown there in the left. The results are similar to what we had before. And here in 3 mass beings between 9 and 10, 10 and 10 to 0.5 and higher than 10.5. The results are all very similar, but we can see that for the lower mass regime, lower that we can sample, we don't go below 9. But for this lower mass regime, the difference between the group galaxies and individual, it's smaller compared to when you go to higher mass. And also, obviously, I mean, as we saw in the beginning, and as we know, the lower mass galaxies, they are more star forming than the higher mass. So these fractions here, if you see the y-axis, they decrease from there to there and to here. So we go to higher mass systems as fraction. These fractions are typically lower too. So Douglas Brandila, who was a PhD student working with me, is a postdoc in São Paulo now. He's finishing a paper on that, and he's more interested in the separate galaxies according to the morphology. And he's investigating different things such as the quenching efficiency, and he shows here for the left here for the each early type galaxies and for the right for late type galaxies. that are in the infall regions of clusters, where we have the individual galaxies and galaxies that are in groups, individual as the dashed line, and the group galaxies, the solid line. And we see that the quenching efficient defined by that equation there, we can detect the difference between the two populations, and even for the late type galaxies, but that effect depends on the morphology, so it's larger for the ATGs. So we have a project to work with that with the JPass survey. I'm not going to details here, but initially we would like to sample the local universe, where we can go down to m star plus 6 with JPass data, but also try to investigate an evolution going to 2.7. Initially, we would like to investigate this region around Able 2199, which is which belongs to the Hercules supercluster. So that's the Hercules supercluster here with lower data. I need to update that using DASI data too, if available in that region. But anyway, so we have the distribution here of individual and group galaxies in this region. So the black circles there, they indicate clusters from the list of Temple et al. 2012. And so we have the individual galaxies surrounding them and the group galaxies and so on. So that's the work that this undergraduate students is involved with, Flavia Vanna. And the problem is that still with this lower data, the problem is that when you go to the JPass data, we have a cut at 41. We don't have sampling below 41, as I was discussing with Roger before. So we can sample this guy here, which is able 2197, but that's a match between JPass photometry and Sloan spectroscopy data. So we miss galaxies here. We have only photometry, we would have obviously more. And obviously, the Hercules supercluster goes all the way to the south. That the way this is going to evolve depends on how the survey grows. If more in array or more in deck, that will be important too. Just want to mention the study that that's the reason why I came here to work with Dr. Yolanda Jimenez Terra, and besides the JPass meeting that we had last week. And so we aim to investigate the intergroup light and the processing effect using the intergroup light. That's a PhD project of this student that started this year, Beatriz Amarante. And the idea is to use groups that are in the footprint of the HSC, SSP data from Osbaro, and also compared to isolated groups and so on, and possibly also perform the comparison to simulation data. And if everything goes right, she will come here next year as a student to visit and collaborate with Yolanda. Okay, I'm almost finishing here. I just want to highlight some problems and difficulties that we have on this type of studies, like problems on preprocessing studies. So this from Dressler 2003, 2013. So it's a similar plot that what I have. I have a density map in the beginning. So we have here delta X and Y, could be array and deck, but showing the spatial distribution of galaxies that they classify as group members that fall into the clusters, and galaxies that are non-group members, what I call individual galaxies that are fall into the clusters. We see some similar results to what I have. It's interesting that they use many of you know, the Dressler and Sheckman test to identify substructures within a cluster. So and these substructures they called group galaxies. That's what they use. But even using his own method, Dressler and collaborators, and they point out that they don't sample galaxies that are in groups with less than 5 members, something that I pointed out before. So that's a lower estimate to the total infalling population. So we need to go to lower systems to correct this deficiency. The way that we selected the group members was using the catalog from Temple et al. 2012, which uses a friends of friend group finder, which is not perfect, but it can go all the way to the pairs and so on. So even work using the friends of friends, you will be limited. We will be incomplete, but I mean, I think it's the best way to go. With X-rays, unfortunately, we can not go all the way down. And also this comment from Kirkner Ulrich from 2012 to 22, where they claim that it's very difficult also to investigate the preprocessing effect in filaments because galaxies in filaments could be a mix of several populations, including group galaxies, backsplash galaxies, and so on. So that's a summary of what we got. I think I'm just going to finish now. Thank you. Bye.
Thank you for the talk. Also, it's plenty of biography to revise, so it's very useful. I wonder when you make the stacking of the result as a function of the fraction of star-forming galaxy as a function of the distance to the center of the cluster. I mean, you are adding or you are stacking the result independent of the cluster mass. Do you think that could be affect the result?
Yes, the sample that we have only have clusters, and the definition that have above 10 to 14 solar masses. That could affect, but I don't remember, but I have a plot here. So thank you for the question. That's it. So that's a fraction of star-forming galaxies for all galaxies with stellar mass. So the full sample that we have, all galaxies with masses above log of mass above 9, but split according to the group, the cluster mass, the hosting cluster mass. So here, here's everything. So the result that we had before, and here for clusters with masses above, between 1 and 3 times 10 to 14 solar masses, between 3 and 5, 10 to 14, and above the most massive ones above 5, 10 to 14 solar masses. So the results got noisier as we go back because we have fewer galaxies, but I didn't check that very much. That's ongoing work, but I think they kind of similar. Yeah, I mean here we have a reduced difference between them. So we're larger or less.
I understand that the different panel is for different range of
cluster mass.
Cluster mass.
Yeah, here's between, I didn't put a label, sorry.
Okay.
Between 1 and 3 times 10 to 14 solar masses, 3 and 3 times 10 to 14, above 5 times 10 to 14 solar masses. And that is everything, above 10 to 14.
Okay. So it's going the sense that it look like that the quenching effect, if we take we can interpret the fraction of star-forming galaxy as the different, as the opposite to the quenching effect. So that means that there, when the mass of the cluster is higher, the efficiency for quenching the star formation galaxy is higher.
I think so, but the result is, for me, it's not as clear as when I show the results according to the group mass, the groups that are infalling to the cluster. But I mean, traced by membership, not mass, not exact mass.
Well, the result that we found with the JPass, that in fact we have most of the in mini JPass is that if you remember, most of the, we don't have a cluster, in fact, only one, there is one big cluster. But what I found was that the efficiency for quenching the star formation in every range of the mass, stellar mass, galaxy stellar mass, increase in the cluster with respect to the group. If the group are not very massive, the quenching is not so efficient. However, when we increase the mass or increase the potential well of the cluster, in that case, the efficiency is significantly higher.
Yeah, no, I agree with that. But there we are dealing with groups. I mean, they are below 10 to 14 solar masses.
Yes.
Here with real clusters above 10 to 14.
Yeah, well,
We had one cluster there that we call
Well-
mini big JPEG, but it has one, it's 10
Yeah,
to 14
yeah.
solar mass, basically. And that was the work of Google.
But because
you explained the other systems, but they are all groups, they are all below 10 to 14.
yeah, that's true. But that's why I asked, because you have more evidence that the effect of the mass of the cluster in the quenching in the efficiency of the quench, the star formation.
I agree. But I think that should be compared to this here. So here we are dealing with groups. So that's what we have groups here. So those are groups that are in the infall regions of clusters. That we are not examining the group as the main system. But we see that there is a dependence with group membership, or in other words, with mass. So the red points have a higher star formation fraction of star formation rate compared to the black ones. So the more massive the group, the more quenched galaxies there are.
But okay, well, we can continue the discussion. It's because I wonder, because this group must belong to a cluster, and I wonder about the mass, the total mass of the cluster. Or at least
Yeah, that's the other
that
result I
belongs,
showed.
because the
Yeah.
number of the group cannot say too much about the total potential where they are hosting.
Yeah,
That's why I was
see.
wondering
Yeah.
about.
that's the other result that was just shown. Yeah.
Yeah, in many of the plots, these and many other plots that you showed, you basically showing on the x-axis the projected radius, right? Now, if I remember correctly, the phase space diagram that you showed, the velocity range is huge, like more than 10 to, not this one. I think there was another one where you were showing the absolute velocities. Yeah. Yeah, this one here. Actually, but anyway, doesn't. I think you go up to 10,000 kilometers per second, if I remember correctly.
No,
on
not
the
10,000.
other plot.
No, there is no plot going to 10,000. It's around at most 2,000 kilometers per second or so, which is typical of massive clusters. So for massive clusters, we have members within normally between plus minus 2,000 kilometers per second, but even like that, this is normalized by velocity expression. So
Yeah, I think it's the other plot actually.
Yeah, so the other plots that I have, those are from hands also, from simulation. What you see, it's between mostly of the guys are between plus minus 2,000 kilometers per second.
But then the question would be with that, velocity range that is, I mean, this 1,000, 2,000 is reasonable. But if you have a large range of velocity dispersion, then what happens is that your projected distance is basically going to be biased, because you're not sure whether or not, because a galaxy can be, at a close to, the cluster center, but then at a very different velocity, and then could be that could induce some kind of bias.
Yeah, no, but I don't know. I can check later, but I think there's no plot going on
No,
the way to 10,000,
I'm
but
destroying it.
it's normally around 2,000 and so. But as we expect, I mean, the membership, as we go outside to the outskirts of clusters, the velocity range diminishes. So the galaxies follow a caustic profile that the velocity diminishes with distance to the center of the cluster due to the reduced velocity escape. Escape velocity. Yeah. So, I know.
So, kind of relating with that question, do you think it would be possible with simulations analyzing how much or up to what extent the trajectories of the infalling groups or galaxies, like for example, in the impact factor, I understand that if you are like infalling into the cluster in a more direct trajectory, you are going to lose velocity material, like more like faster, like if you are following like a more tangential trajectory. So do you think that could be like an important effect that could be somehow quantified with simulations?
Yes, as we have like the information and the full phase space diagram in 6D, you can try to track the orbits backwards to the past and try to reconstruct the orbits. I'm not too, I don't really work with that, but I think it's possible. So you can, if you can reconstruct it, you can see the effect of the different things on the evolution of the galaxy and the way that they are affected by the constant galaxies falling in a way or falling more tangentially, the run pressure stripping will be different, for instance.
Yeah, but in that case, that can be a bit more tricky. I mean, if the trajectory is, let's say, more tangential component, you're not going to have backsplash galaxies.
No, yeah.
So the difference will be not so evident.
Yeah. I don't know what would be the percentage of galaxies that would have more like a tangential orbit, but in that case, yeah, if the galaxy to go through the cluster would take a longer time. Yeah. But I mean, just with simulation, try to do that.
Sure.
Okay.
Thank you. I'm sorry I missed half of the talk, but so I think there is a paper on this related to this for Jonathan Hernandez Fernandez and Haynes, and also in relation to just this question: where are these galaxies located when they are either backsplash or entering in the toward the cluster? But this is not my question. I think my question is the data that you have, which was a simulation, by the way. The data that you have shown are from, I mean, which are the data from? The data you have shown?
It's lower data. It's low on data.
It's lower.
Yeah.
Okay. So you use for the fraction, for the definition of star-forming galaxies, you use the emission line, or you use color? What did you?
I use the MPH Johns Hopkins catalog. I think it's called set fitting. Yeah. But,
so the set fitting.
Yeah.
So that's include. But
they correct for the fiber and
yeah. But I mean,
yeah.
So they could be, I mean, post star or something kind of like these galaxies will be there, or just start forming, actively start forming.
No, there could be some post star rush too. Okay. I didn't dig into that too. Because, but I mean, we separate them and see.
Because I remember well, my main point was whether well, there is this paper by Rines and collaborators, and later they use just H alpha. So what I see that in you just H alpha, but then you are using the classification from the set fitting.
Yeah.
Okay. So the point is that apparently from the figures you have shown, the behavior is much the same whether you are using. I mean, I have seen you remember the Rines plots and your plots, and also then you see when you go 2 times the R200, more or less you reach 20% near the field or something like that. which is more or less that. So what was published those days. So the point is not important whether they are groups or they are clusters or they are the info region of a cluster. You know what I mean? Whether the info region of a cluster is very big. So whether your groups are isolated, as you mentioned, or they are near a cluster, it doesn't matter. This is not important for the analysis.
No, it is. Yeah. So I showed this picture just to try to emphasize that the regions are huge. So we go to 5 or 200 actually. But so we split galaxies that are in the 4 regions of clusters between galaxies that are what we call group galaxies, detected by friends of friends algorithms, or individual galaxies, those that are single galaxies in this catalog of friends of friends. They are not part of a group. But it makes difference, I think. I'm not sure if I understood the question, but it makes difference if they are individual galaxies or group galaxies.
I missed this part.
No, I was not sure if I understood the question.
Yeah. Well,
but I mean, on what regards post-starburst galaxies, we didn't separate a subpopulation of the star-forming galaxies, such as a post-starburst. That could make a difference too. To see where
they are different.
So we just use this separation here, using the star formation weight from set fit.
Okay, because they are completely different. So what you saw in the some time ago, we published a paper on it was in Ever 1367 and Coma, and we see that in filaments, I mean, most of the processing we saw was in the filaments, not in the infra region as a general. And the number of filaments were not very big, were just 2 or 3 or something like that. So I don't know whether this has changed. This picture has changed over the year, or we are more or less. So the highest level of processing that we saw those days was in smaller groups, very small groups, 3 or elements, something like that, in filaments, not in the info region as a whole. So is that the picture is the same, or this?
I don't know. How do I say? The work that I showed that's published, it's about the galaxies in the info region separated as individual or group galaxies. There are some results here that I need to have time to finish writing the paper. That we do some other things like splitting mass, also in stellar mass, but also the cluster mass, as I was showing to Rosa. But we also check the fraction of galaxies that are in filaments. But I mean, from the populations that you have, we don't try to check all the galaxies that are in filaments and divide in different populations. We see for all the individual galaxies that are in the info region of clusters, what's the fraction of those galaxies? Those are the blue ones, the individual galaxies that are in filaments in the surrounding regions of clusters. So that's how they grow. And from the group galaxies that are in the info regions, what's the fraction of group galaxies that are in filaments? So that goes, I think it agrees with what you said. So most of the group galaxies inside the 500-200, they are part of filaments. So 55% or so, no matter the ratio.
Yeah, that's consistent.
So that's different from what Kuchner would gets, but she's doing the other way around. She's getting from all the galaxies within the filament population, but she divides in different populations such as backsplash, group galaxies, and I think individual too, or some other populations. So the group fraction that she gets and they get, it's smaller, but they are measuring something different than what I measured here. So what I'm saying is that most of the group galaxies that are coming to clusters, they're coming through filaments. So most of the preprocessing is happening in filaments, as you said, I guess.
I have a question. Very nice talk, interesting. So I wonder, so you're using the Temple catalog, right, to classify membership. So have you tried to use other catalogs of group members to see if in those regions where there are nuance and time it's catalog dependent?
No, I didn't. I actually talked to Temple once because at some point I tried the YAM catalog at the beginning of this work. We tried the YAM catalog from 2007, updated at some different time. And And then I got a catalog from Temple 2012. I still work with that, but there are another version from 2018, I guess, from Temple collaborators. I talked to him once and said, oh, there is a little bit difference in the sample definition, but not too much. So it wouldn't affect the results. Or from other group catalogs from other groups, they didn't try exact the Yan catalog, but I did. But in the central part, it's very hard to detect the galaxies that belong to groups because they are mixed already with the cluster population, and also there is a problem that the group is very close to if a group traverses the cluster, we expect that the group is going to be destroyed most of the time. So if you see a backsplash gaps that belong to a group in the past, they are probably not grouped any longer. And especially for the filaments here, those fractions they are within F200. I don't put my hand in the fire for that. But outside, yes, but not really. Also to assign a galaxy to a filament when you get closer to the cluster, it's hard. The filaments get thicker, but I guess the velocities also affect the definition. So anyway, sorry, I didn't try it. We tried that again.
What's your question? Did you make the same comparison, but we using the morphological type by Dominguez Sanchez? Which was the difference between the star formation of using the axis with star formation or with morphological type? I think that I didn't understand.
Yeah, in the paper that we published last year, the main difference is that the typical values of the fractions of late type galaxies were larger, but I think that larger than the fraction of star forming galaxies. I think that's mainly due to the not so rigorous way as we split latent type galaxies in the paper that we published. So for this work here that we've been finishing, we redefined the separation using the work of Dominguez Sanchez, and the fractions are more similar to the fraction of star forming galaxies. So that conclusion that we put that the morphological transformation happens in a larger time scale than the quenching process. That might be true, but I don't think the results are too significant to help on that. Maybe simulations also help characterize that. So from this updated work, the fractions are similar to their star-forming fraction.
Any other questions? And I don't believe anyone on Zoom has questions.
Do we have time for more questions? Because I have one.
You can ask a quick question.
Okay.
Make it simple.
Now that you came back to the morphological type issue, so how did you then?
Was about algebra.
How did you then determine or identify the star-forming galaxies in this? What indicator did you choose?
Sorry, talk about it.
In all the samples, how do you identify star-forming galaxies?
That plot that I showed you, Pepe, just using the star formation rate versus stellar mass plot. Sorry. Yeah. So we use this relation from Dressler et al. 2020, also based on Sloan data, the local universe, which is this line here. So galaxies above this line we call star forming, and galaxies below this line we call passive. Just using that. Doesn't make much of a difference of a definition. Before we were using specific star formation rate, we had like a I forgot the name.
Yeah, I guess
the distribution we could draw a line there.
I guess the question was more like how were the star formation rate here measured or estimated?
Oh, it's a set fitting. That's a set fitting. Yes. To the spectrum, but they correct for the fiber, the size of the fiber too. So.
Okay.
But it's just set fitting.
Well, then I get depending on the how, I mean, what indicator you choose, you might get.
I don't think it makes too much of a difference. Here, for instance, Haynes et al. They use star formation from the infrared. So, and also they use star formation indicated from a color diagram, and it doesn't make a difference. So I don't know which is which, but one is in pink and the other one is in red. The pink points and the red points. So those are the two indicators. So one of them is higher than the other, but the main conclusion is that they grow when you go outside and never reach the field.
But in fact, depends on the star forming main sequence that you use for segregate the star forming from passive galaxy. Quench galaxy. Because in fact, I suppose that the double line that is because it is the corresponding to the Green Valley galaxy, more or less.
So they call here passive, Green Valley, and star forming. In this work, I only use this line to separate between. We call everything above the first line as star forming, so Green Valley 2. In the work of Douglas Bambrilla et al. 2023, he actually considered the three populations: the Green Valley, the star forming, and for different goals, for different work that he did, and the passive. But I mean, I was more concerned to the results that measure the fraction of passive galaxies or star forming, and I'm more worried about splitting between passive and star forming, not the Green Valley population. So, but I mean, yeah. So this line could be a little bit higher here. I don't know if that's what you mean. But,
no, well, what I mean is that the slope and the 0 point of the correlation depends on different analysis.
Yeah,
so,
but
because it is dependent of the stellar mass also, and the result you are splitting by a stellar mass of the galaxy stellar mass could be some difference. I don't know.
Yeah, but as you have a line like that, the dependence in stellar mass is there.
That's what I mean.
Yeah, okay. Yeah. But I mean, we show the results globally and now in beings of stellar mass too. So. But yeah. Yeah, but before we were using like a specific star formation rate distribution. So it's a bimodal distribution and make a cut there to separate the passive and star forming. Like Wetzel et al. 2010 or so, 11, I don't remember. And the separation between the two populations, they are a little bit different. The numbers are globally similar, but there is small difference. But the results that we get globally, they don't change. The fractions are forming galaxies. Unless you use something very, very different. So, I mean, if we were using this line here, star forming passive, that would go the way around. So, but it does depend, yes. I agree.
So let's thank our speaker again. All right, and I stopped the transmission. So